taking care of an 80-year-old, and something was going to get them pretty soon anyway. And so you lose a patient like that, and it was part of the natural course of what is expected of them in the coming years, regardless. Taking care of, a father of 2 or 3, 4 young kids, someone in their 30s that didn't have it coming, and they show up in your ER having their first seizure of their life, and lo and behold, they've got a huge malignant, inoperable, or incurable brain tumor. You can only do that, I think, a handful of times before it really starts eating away at your armor. Or a young mother that shows up that has a giant hemorrhage in her brain that she's not going to survive from, and they bring her 4-year-old daughter in to say goodbye one last time before they turn the ventilator off. That the great Henry Marsh is an English neurosurgeon who said it best. I think he says that every neurosurgeon carries with them a private graveyard, and I definitely feel that. Especially with young parents, that kills me. They had a lot more to give. The loss of those people specifically has a knock-on effect that's going to make the world worse for people for a long time, and it's just hard to feel powerless in the face of that. And that's where I think you have to be borderline evil to fight against a company like Neuralink, or to constantly be taking pot shots at us, because what we're doing is to try to fix that stuff. We're trying to give people options to reduce suffering. We're trying to take the pain out of life that broken brains brings in. And this is just our little way that we're fighting back against entropy, I guess.
Yeah, that's the amount of suffering that's endured when some of the things that we take for granted that our brain is able to do is taken away is immense. And to be able to restore some of that functionality is a real gift.
Yeah. We're just starting. We're gonna do so much more.
Well, can you take me through the full procedure for implanting, say, the N1 chip in Neuralink?
Yeah, it's a really simple, straightforward procedure. The human part of the surgery that I do is dead simple. It's one of the most basic neurosurgery procedures imaginable, and I think there's evidence that some version of it has been done for thousands of years. There are examples, I think, from ancient Egypt of healed or partially healed trephinations, and from Peru, or ancient times in South America, where these proto-surgeons would drill holes in people's skulls, presumably to let out the evil spirits, but maybe to drain blood clots. And there's evidence of bone healing around the edge, meaning the people at least survive some months after a procedure. And so what we're doing is that we are making a cut in the skin on the top of the head over the area of the brain that is the most potent representation of hand intentions. And so if you are an expert concert pianist, this part of your brain is lighting up the entire time you're playing. We call it the hand knob.
The hand knob.
Yeah.
So it's all the finger movements, all of that is just firing away.
Yep. There's a little squiggle in the cortex right there. One of the folds in the brain is kind of doubly folded right on that spot. And so you can look at it on an MRI and say, that's the hand knob. And then you do a functional test in a special kind of MRI called a functional MRI, fMRI. And this part of the brain lights up when people, even quadriplegic people whose brains aren't connected to their finger movements anymore, they imagine finger movements, and this part of the brain still lights up. So we can ID that part of the brain in anyone who's preparing to enter our trial and say, okay, that part of the brain we confirm is your hand intention area. And so I'll make a little cut in the skin. We'll flap the skin open, just like kind of opening the hood of a car, only a lot smaller. Make a perfectly round 1-inch diameter hole in the skull. Remove that bit of skull. Open the lining of the brain, the covering of the brain. It's like a little bag of water that the brain floats in. And then show that part of the brain to our robot. And then this is where the robot shines. It can come in and take these tiny, much smaller than human hair electrodes and precisely insert them into the cortex, into the surface of the brain to a very precise depth in a very precise spot that avoids all the blood vessels that are coating the surface of the brain. And after the robot's done with its part, then, the human comes back in and puts the implant into that hole in the skull and covers it up, screwing it down to the skull and sewing the skin back together. So the whole thing is, a few hours long. It's extremely low risk compared to the average neurosurgery involving the brain that might, say, open up a deep part of the brain or manipulate blood vessels in the brain. This opening on the surface of the brain with only cortical microinsertions carries significantly less risk than a lot of the tumor or aneurysm surgeries that are routinely done.
So cortical microinsertions that are via robot and computer vision are designed to avoid the blood vessels.
Exactly.
So I know you're a bit biased here, but let's compare human and machine.
Sure.
So what are human surgeons able to do well, and what are robot surgeons able to do well at this stage of our human civilization development?
Yeah, that's a good question. Humans are general purpose machines. We're able to adapt to unusual situations. We're able to change the plan on the fly. I remember well a surgery that I was doing many years ago down in San Diego where the plan was to open a small hole behind the ear and go reposition a blood vessel that had come to lay on the facial nerve, the trigeminal nerve, the nerve that goes to the face. When that blood vessel lays on the nerve, it can cause just intolerable, horrific shooting pain that people describe like being zapped with a cattle prod. And so the beautiful, elegant surgery is to go move this blood vessel off the nerve. The surgery team, we went in there and started moving this blood vessel and then found that there was a giant aneurysm on that blood vessel that was not easily visible on the pre-op scans. And so the plan had to dynamically change, and that the human surgeons had no problem with that. We're trained for all those things. Robots wouldn't do so well in that situation, at least in their current incarnation. Fully robotic surgery, like the electrode insertion portion of the Neuralink surgery, it goes according to a set plan. And so the humans can interrupt the flow and change the plan, but the robot can't really change the plan midway through. It operates according to how it was programmed and how it was asked to run. It does its job very precisely, but not with a wide degree of latitude in how to react to changing conditions.
So there could be just a very large number of ways that you could be surprised as a surgeon. When you enter a situation, there could be subtle things that you have to dynamically adjust to.
Correct.
And robots are not good at that.
Currently.
I
think we are at the dawn of a new era with AI of the parameters for robot responsiveness to be dramatically broadened. Right? I mean, you can't look at a self-driving car and say that it's operating under very narrow parameters. If a chicken runs across the road, it wasn't necessarily programmed to deal with that specifically, but a Waymo or a self-driving Tesla would have no problem reacting to that appropriately. And so surgical robots aren't there yet, but give it time.
And then there could be a lot of sort of like semi-autonomous possibilities of maybe a robotic surgeon could say this situation is perfectly familiar or the situation is not familiar. And in the not familiar case, a human could take over. But basically like be very conservative and saying, okay, this for sure has no issues, no surprises, and then let the humans deal with the surprises, with the edge cases, all that.
Yeah.
That's one possibility. So, like, you think eventually, you'll be out of the job. Well, you being neurosurgeon, your job being neurosurgeon. Humans, there will not be many neurosurgeons left on this earth.
I'm not worried about my job in the course of my professional life. I think I would tell my kids not necessarily to go in this line of work, depending on how things look in 20 years.
It's so fascinating because if I have a line of work, I would say it's programming. And if you ask me, like, for the last, I don't know, 20 years, what I would recommend for people, I would tell them, yeah, go. Like, there's just, you will always have a job if you're a programmer because there's more and more computers and all this kind of stuff, and it pays well. But then you realize these large language models come along and they're really damn good at generating code.
Yeah.
So it's overnight you could be surprised, like, wow, like, what is the contribution of the human really? But then you start to think, okay, it does seem that humans have ability, like you said, to deal with novel situations. And in the case of programming, it's the ability to kind of come up with novel ideas to solve problems. It seems like machines aren't quite yet able to do that. And when the stakes are very high, when it's life critical, as it is in surgery, especially neurosurgery, then it starts, the stakes are very high for a robot to actually replace a human. But it's fascinating that in this case of Neuralink, there's a human-robot collaboration.
Yeah. I do the parts it can't do, and it does the parts I can't do. And we are friends.
I saw that there's a lot of practice going on. So, I mean, everything in Neuralink is tested extremely rigorously. But one of the things I saw that there's a proxy on which the surgeries are performed.
Yeah.
So this is both for the robot and for the human, for everybody involved in the entire pipeline.
Yep.
What's that like, practicing the surgery?
It's pretty intense. So there's no analog to this in human surgery. Human surgery is sort of this artisanal craft that's handed down directly from master to pupil over the generations.
Yes.
I mean, literally the way you learn to be a surgeon on humans is by doing surgery on humans. I mean, first you watch your professors do a bunch of surgery, and then finally they put, the trivial parts of the surgery into your hands, and then the more complex parts. And as your understanding of the point and the purposes of the surgery increases, you get more responsibility in the perfect condition. It doesn't always go well. In Neuralink's case, the approach is a bit different. We, of course, practiced as far as we could on animals. We did hundreds of animal surgeries. And when it came time to do the first human, we had just an amazing team of engineers build incredibly lifelike models. One of the engineers, Fran Romano in particular, built a pulsating brain in a custom 3D printed skull that matches exactly the patient's anatomy, including their face and scalp characteristics. And so when I was able to practice that, I mean, it's as close as it really reasonably should get to being the real thing in all the details, including, having a mannequin body attached to this custom head. And so when we were doing the practice surgeries, we'd wheel that body into the CT scanner and take a mock CT scan and wheel it back in and conduct all the normal safety checks, verbally, stop. This patient, we're confirming his identification is mannequin number, blah, blah, blah. And then opening the brain in exactly the right spot using standard operative neuronavigation equipment, standard surgical drills in the same OR that we do all of our practice surgeries in at Neuralink, and having the skull open and have the brain pulse, which adds a degree of difficulty for the robot to, perfectly precisely plan and insert those electrodes to the right depth and location. And so, we kind of broke new ground on how extensively we practiced for this surgery.
So there was a historic moment, a big milestone for Neuralink, in part for humanity, with the first human getting a Neuralink implant in January of this year. Take me through the surgery on Noland. What did it feel like to be part of this?
Yeah. Well, we're lucky to have just incredible partners at the Barrow Neurologic Institute. They are, I think, the premier neurosurgical hospital in the world. They made everything as easy as possible for the trial to get going, and helped us immensely with their expertise on how to arrange the details. It was a much more high pressure surgery in some ways. I mean, even though the outcome wasn't particularly in question in terms of our participants' safety, the number of observers,
Right.
the number of people, there's conference rooms full of people watching live streams in the hospital, rooting for this to go perfectly. And that just adds pressure that is not typical for even the most intense production neurosurgery, say removing a tumor or, placing deep brain stimulation electrodes. And it had never been done on a human before. There were unknown unknowns. And so definitely a moderate pucker factor there for the whole team, not knowing if we were going to encounter, say, a degree of brain movement that was unanticipated, or a degree of brain sag that took the brain far away from the skull and made it difficult to insert, or some other unknown problem. Fortunately, everything went well, and that surgery was one of the smoothest outcomes we could have imagined.
Were you nervous? I mean, you're
Extremely.
a bit of a quarterback in the Super Bowl kind of situation.
Extremely nervous. Extremely. I was very pleased when it went well, and when it was over. Looking forward to number 2.
Yeah. Even with all that practice, all of that, just you've never been in a situation that's so high stakes in terms of people watching.
Yeah.
And we should also probably mention, given how the media works, a lot of people, maybe in a dark kind of way, hoping it doesn't go well.
Well, I think wealth is easy to hate, or envy, or whatever. And I think there's a whole industry around driving clicks, and bad news is great for clicks. And so any way to take an event and turn it into bad news is going to be really good for clicks.
It just sucks because I think it puts pressure on people. It discourages people from trying to solve really hard problems, because to solve hard problems, you have to go into the unknown. You have to do things that haven't been done before, and you have to take risks.
Yeah.
Calculated risks. You have to do all kind of safety precautions, but risks nevertheless. And I just wish there would be more celebration of that, of the risk taking, versus people just waiting on the sidelines, waiting for failure.
Yeah.
And then pointing out the failure. It sucks, but in this case, it's really great that everything went just flawlessly. But it's unnecessary pressure, I would say.
Now that there's a human with literal skin in the game, there's a participant whose well-being rides on this doing well. You have to be a pretty bad person to be rooting for that to go wrong.
Yeah.
And so, hopefully people look in the mirror and realize that at some point.
So did you get to actually front row seat, watch the robot work? What, you get to see the whole thing?
Yeah. I mean, because an MD needs to be in charge of all of the medical decision making throughout the process. I unscrubbed from the surgery after exposing the brain and presenting it to the robot, and placed the targets on the robot software interface that tells the robot where it's going to insert each thread. That was done with my hand on the mouse for whatever that's worth.
So you were the one placing the targets?
Yeah.
Oh, cool. So like the robot with the computer vision provides a bunch of candidates, and you kind of finalize the decision.
Right. The software engineers are amazing on this team, and so they actually provided an interface where you can essentially use a lasso tool and select a prime area of brain real estate, and it will automatically avoid the blood vessels in that region and automatically place a bunch of targets. So that allows the human robot operator to select really good areas of brain and make dense applications of targets in those regions. The regions we think are going to have the most high fidelity representations of finger movements and arm movement intentions.
I've seen like images of this, and for me with OCD, it's for some reason a really pleasant. I think there's a subreddit called Oddly Satisfying.
Yeah, love that subreddit.
It's oddly satisfying to see the different target sites avoiding the blood vessels, and also maximizing like the usefulness of those locations for the signal. It just feels good. It's like
As a person who has a visceral reaction to the brain bleeding, I can tell you it's extremely satisfying watching the electrodes themselves go into the brain and not cause bleeding.
Yeah. So you said the feeling was of relief when everything went perfectly.
Yeah.
How deep in the brain can you currently go and eventually go? Let's say on the Neuralink side, it seems the deeper you go in the brain, the more challenging it becomes.
Yeah. So talking broadly about neurosurgery, we can get anywhere. It's routine for me to put deep brain stimulating electrodes near the very bottom of the brain, entering from the top and passing about a 2 millimeter wire all the way into the bottom of the brain. And that's not revolutionary. A lot of people do that. And we can do that with very high precision. I use a robot from Globus to do that surgery, several times a month. It's pretty routine.
What are your eyes in that situation? What are you seeing? What kind of technology can you use to visualize where you are to light your way?
Yeah, so it's a cool process on the software side. You take a preoperative MRI that's extremely high resolution data of the entire brain. You put the patient to sleep, put their head in a frame that holds the skull very rigidly, and then you take a CT scan of their head while they're asleep with that frame on, and then merge the MRI and the CT in software. You have a plan based on the MRI where you can see these nuclei deep in the brain. You can't see them on CT, but if you trust the merging of the two images, then you indirectly know on the CT where that is, and therefore indirectly know where, in reference to the titanium frame screwed to their head, those targets are. And so this is 60s technology to manually compute trajectories given the entry point and target, and dial in some goofy looking titanium actuators with manual actuators with little tick marks on them. The modern version of that is to use a robot, just like a little KUKA arm you might see at building cars at the Tesla factory. This small robot arm can show you the trajectory that you intended from the pre-op MRI and establish a very rigid holder through which you can drill a small hole in the skull and pass a small rigid wire deep into that area of the brain that's hollow, and put your electrode through that hollow wire and then remove all of that except the electrode. So you end up with the electrode very, very precisely placed far from the skull surface. Now that's standard technology that's already, been out in the world for a while. Neuralink right now is focused entirely on cortical targets, surface targets, because there's no trivial way to get, say, hundreds of wires deep inside the brain without doing a lot of damage. So your question, what do you see? Well, I see an MRI on a screen. I can't see everything that DBS electrode is passing through on its way to that deep target. And so it's accepted with this approach that there's going to be about 1 in 100 patients who have a bleed somewhere in the brain as a result of passing that wire blindly into the deep part of the brain. That's not an acceptable safety profile for Neuralink. We start from the position that we want this to be dramatically, maybe 2 or 3 orders of magnitude safer than that. Safe enough, really, that you or I, without a profound medical problem, might on our lunch break someday say, "Yeah, sure, I'll get that. I've been meaning to upgrade to the latest version."
Yeah.
And so the safety constraints given that are high. And so we haven't settled on a final solution for arbitrarily approaching deep targets in the brain.
It's interesting because you have to avoid blood vessels somehow. You have to, maybe there's creative ways of doing the same thing, like mapping out high resolution geometry of blood vessels, and then you can go in blind. But how do you map out that in a way that's super stable? There's a lot of interesting challenges there, right?
Yeah.
But there's a lot to do on the surface, luckily.
Exactly. So we've got vision on the surface. We actually have made a huge amount of progress sewing electrodes into the spinal cord as a potential workaround for a spinal cord injury that would allow a brain-mounted implant to translate motor intentions to a spine-mounted implant that can affect muscle contractions in previously paralyzed arms and legs.
That's mind-blowing. That's just incredible. So the effort there is to try to bridge the brain to the spinal cord to the peripheral nervous system. So how hard is that to do?
We have that working in very crude forms in animals.
That's amazing.
Yeah, we've done
so similar to with Nolan, where he's able to digitally move the cursor. Here you're doing the same kind of communication, but with the actual effectors that you have.
Yeah.
That's fascinating.
Yeah. So we have anesthetized animals doing grasp and moving their legs in a sort of walking pattern. Again, early days, but the future is bright for this kind of thing. And people with paralysis should look forward to that bright future. They're going to have options.
Yeah, and there's a lot of sort of intermediate or extra options where you take an Optimus robot, like the arm, and to be able to control the arm.
Yeah.
The fingers, the hands, and the arm.
Sure.
As a prosthetic. For example,
exoskeletons are getting better too.
Exoskeletons. Yeah, so that goes hand in hand. Although I didn't quite understand until thinking about it deeply and doing more research about Neuralink, how much you can do on the digital side. So there's digital telepathy.
Yeah.
I didn't quite understand that you can really map the intention, as you described in the hand knob area, that you can map the intention. Just imagine it. Think about it. That intention can be mapped to actual action in the digital world.
Right.
And now more and more, so much can be done in the digital world that it can reconnect you to the outside world. It can allow you to have freedom, have independence if you're a quadriplegic.
Yeah.
That's really powerful. You can go really far with that.
Yeah. Our first participant he's incredible. He's breaking world records left and right.
And he's having fun with it. It's great. Yeah. Just going back to the surgery, your whole journey, you mentioned to me offline you have surgery on Monday. So you're doing surgery all the time.
Yeah.
Maybe the ridiculous question, what does it take to get good at surgery?
Practice, repetitions. You just, same with anything else. there's a million ways of people saying the same thing and selling books saying it, but do you call it 10,000 hours? Do you call it, spend some chunk of your life, some percentage of your life focusing on this, obsessing about getting better at it? Repetitions, humility, recognizing that you aren't perfect at any stage along the way, recognizing you've got improvements to make in your technique, being open to feedback and coaching from people with a different perspective on how to do it. And then just the constant will to do better. That fortunately, if you're not a sociopath, I think your patients bring that with them to the office visits every day. They, force you to want to do better all the time.
Yeah, to step up. I mean, it's a real human being that you can help.
Yeah.
So every surgery, even if it's the same exact surgery, is there a lot of variability between that surgery and a different person?
Yeah, a fair bit. I mean, a good example for us is the angle of the skull relative to the normal plane of the body axis of the skull over hand knob is pretty wide variation. I mean, some people have really flat skulls and some people have really steeply angled skulls over that area. And that has, consequences for how their head can be fixed in sort of the frame that we use, and how the robot has to approach the skull. And people's bodies are built as differently as the people you see walking down the street. As much variability in body shape and size as you see there, we see in brain anatomy and skull anatomy. There are some people who we've had to kind of exclude from our trial for having skulls that are too thick or too thin, or scalp that's too thick or too thin. I think, we have like the middle 97% or so of people, but you can't account for all human anatomy variability.
How much like mushiness and mess is there? Because I, taking biology classes, the diagrams are always really clean and crisp. Neuroscience, the pictures of neurons are always really nice and very. But whenever I look at pictures of like real brains, they're all, I don't know what is going on.
Yeah.
So how much are biological systems in reality? Like, how hard is it to figure out what's going on?
Not too bad. Once you really get used to this, that's where experience and skill and education really come into play. Is if you stare at 1,000 brains, it becomes easier to kind of mentally peel back the, say, for instance, blood vessels that are obscuring the sulci and gyri, kind of the wrinkle pattern of the surface of the brain. Occasionally, when you're first starting to do this and you open the skull, it doesn't match what you thought you were going to see based on the MRI. And with more experience, you learn to kind of peel back that layer of blood vessels and see the underlying pattern of wrinkles in the brain, and use that as a landmark for where you are.
The wrinkles are a landmark? So like...
Yeah. So I was describing hand knob earlier. That's a pattern of the wrinkles in the brain. It's sort of this sort of Greek letter omega shaped area of the brain.
So you could recognize the hand knob area? Like if I show you 1,000 brains and give you like 1 minute with each, you'd be like, yep, that's that.
Sure.
And so there is some uniqueness to that area of the brain, like in terms of the geometry, the topology of the thing.
Yeah.
Where is it about in the...
It's so you have this strip of brain running down the top, called the primary motor area. And I'm sure you've seen this picture of the homunculus laid over the surface of the brain, the weird little guy with huge lips and giant hands. That guy sort of lays with his legs up at the top of the brain, and face, arm areas farther down, and then some kind of mouth, lip, tongue areas farther down. And so the hand is right in there, and then the areas that control speech, at least on the left side of the brain, in most people are just below that. And so any muscle that you voluntarily move in your body, the vast majority of that references that strip, or those intentions come from that strip of brain, and the wrinkle for hand knob is right in the middle of that.
And vision is back here.
Yep.
Also close to the surface.
Vision's a little deeper. And so, this gets to your question about how deep can you get. To do vision, we can't just do the surface of the brain. We have to be able to go in, not as deep as we'd have to go for DBS, but maybe a centimeter deeper than we're used to for hand insertions. And so that's, work in progress. That's a new set of challenges to overcome.
By the way, you mentioned the Utah array, and I just saw a picture of that, and that thing looks terrifying.
Yeah,
because it's because it's rigid, and then if you look at the threads, they're flexible. What can you say that's interesting to you about that kind of approach of the flexible threads to deliver the electrodes next to the neurons?
Yeah, I mean, the goal there comes from experience. I mean, we stand on the shoulders of people that made Utah arrays and used Utah arrays for decades before we ever even came along. Neuralink arose partly, this approach to technology arose out of a need recognized after Utah arrays would fail routinely because the rigid electrodes, those spikes that are literally hammered using an air hammer into the brain, those spikes generate a bad immune response that encapsulates the electrode spikes in scar tissue, essentially. And so one of the projects that was being worked on in the Anderson lab at Caltech when I got there was to see if you could use chemotherapy to prevent the formation of scar. It's like, things are pretty bad when you're jamming a bed of nails into the brain and then treating that with chemotherapy to try to prevent scar tissue. It's like, maybe we've gotten off track here, guys. Maybe there's a fundamental redesign necessary. And so Neuralink's approach of using highly flexible, tiny electrodes avoids a lot of the bleeding, avoids a lot of the immune response that ends up happening when rigid electrodes are pounded into the brain. And so what we see is our electrode longevity and functionality and the health of the brain tissue immediately surrounding the electrode is excellent. I mean, it goes on for years now in our animal models.
What do most people not understand about the biology of the brain? We'll mention the vasculature. That's really interesting.
I think the most interesting, maybe underappreciated fact is that it really does control almost everything. I mean, I don't know, for an out of the blue example, imagine you want a lever on fertility. You want to be able to turn fertility on and off. I mean, there are legitimate targets in the brain itself to modulate fertility. Say, blood pressure. You want to modulate blood pressure. There are legitimate targets in the brain for doing that. Things that aren't immediately obvious as brain problems are potentially solvable in the brain. And so I think it's an underexplored area for primary treatments of all the things that bother people.
That's a really fascinating way to look at it. Like, there's a lot of conditions we might think have nothing to do with the brain, but they might just be symptoms of something that actually started in the brain. The actual source of the problem, the primary source is something in the brain.
Yeah, not always. I mean, their kidney disease is real, but there are levers you can pull in the brain that affect all of these systems.
There's knobs.
Yeah.
On-off switches and knobs in the brain, from which this all originates. Yeah. Would you have a Neuralink chip implanted in your brain?
Yeah. I think use case right now is use a mouse, right? I can already do that. And so there's no value proposition. On safety grounds alone, sure, I would do it tomorrow.
You say the use case of the mouse. Because after like researching all this, and part of it is just watching Nolan have so much fun. If you can get that bits per second like really high with the mouse, like being able to interact, because if you think about the way on the smartphone, the way you swipe, that was transformational.
Yeah.
How we interact with the thing. It's subtle. You don't realize it, but to be able to touch a phone and to scroll with your finger, that's like, that changed everything. People were sure you need a keyboard to type. And there's a lot of HCI aspects to that changed how we interact with computers. So there could be a certain rate of speed with the mouse that would change everything. Yeah. It's like you might be able to just click around a screen extremely fast. And that, I can see myself getting the Neuralink for much more rapid interaction with the digital devices. Yeah.
I think recording speech intentions from the brain might change things as well. You know, the value proposition for the average person. A keyboard is a pretty clunky human interface, requires a lot of training. It's, you know, highly variable in the maximum performance that the average person can achieve. I think taking that out of the equation and just having a natural, you know, word to computer interface might change things for a lot of people.
It'd be hilarious if that is the reason people do it. Even if you have speech to text that's extremely accurate, it currently isn't.
Right.
But it's say gotten super accurate. It'd be hilarious if people went for Neuralink just so you avoid the embarrassing aspect of speaking, like looking like a douchebag speaking to your phone in public, which is a real, like, that's a real constraint.
Yeah. I mean, with a bone conducting case, that can be an invisible headphone, say, and the ability to think words into software and have it respond to you. You know, that starts to sound sort of like embedded superintelligence. You know, if you can silently ask for the Wikipedia article on any subject and have it read to you without any observable change happening in the outside world. You know, for one thing, standardized testing is obsolete.
Yeah. If it's done well on the UX side, it could change. I don't know if it transforms society, but it really can create a kind of shift in the way we interact with digital devices in the way that a smartphone did. Yeah, I would, just having to look into the safety of everything involved, I would totally try it. So it doesn't have to go to some like incredible thing where you have it connects your vision or to some other, like it connects all over your brain. That could be like just connecting to the hand knob. You might have a lot of interesting interaction, human computer interaction possibilities.
Yeah,
that's really interesting.
Yeah, and the technology on the academic side is progressing at light speed here. I think there was a really amazing paper out of UC Davis, Sergei Stavitsky's lab, that basically made an initial solve of speech decode. It was something like 125,000 words that they were getting with, you know, very high accuracy, which is...
So you're just thinking the word?
Yeah.
Thinking the word and you're able to get it.
Yeah.
Oh, boy. Like you have to have the intention of speaking it.
Right.
So like do that inner voice. Man, it's so amazing to me that you can do the intention to signal mapping. All you have to do is just imagine yourself doing it. And if you get the feedback that it actually worked, you can get really good at that. Like your brain will first of all adjust, and you develop it like any other skill.
Yeah.
Like touch typing, you develop in that same kind of way. That is to me, it's just really fascinating.
Yeah.
To be able to even to play with that. Honestly, like I would get a Neuralink just to be able to play with that. Just to play with the capacity, the capability of my mind to learn this skill. It's like learning the skill of typing or learning the skill of moving a mouse. It's another skill of moving the mouse, not with my physical body, but with my mind.
I can't wait to see what people do with it. I feel like we're cavemen right now. We're like banging rocks with a stick and thinking that we're making music. At some point, when these are more widespread, there's going to be the equivalent of a piano that someone can make art with their brain in a way that we didn't even anticipate. I'm looking forward to it.
Give it to like a teenager. Like anytime I think I'm good at something, I'll always go to like, I don't know, even with the bits per second of playing a video game, you realize you give it to a teenager, you give a Neuralink to a teenager, just a large number of them, the kind of stuff they get good at stuff. They're gonna get like hundreds of bits per second.
Yeah,
even just with the current technology.
Probably.
Just because it's also addicting. How the number go up aspect of it, of like improving and training, because it's almost like a skill. And plus there's the software on the other end that adapts to you. And especially if the adapting procedure, the algorithm becomes better and better and better, you like learning together.
Yeah, we're scratching the surface on that right now. There's so much more to do.
So on the complete other side of it, you have an RFID chip implanted in you.
Yeah.
So I hear. Nice. So this is
a little subtle thing.
It's a passive device that you use for unlocking like a safe with top secrets, or what do you use it for? What's the story behind it?
I'm not the first one. There's there's this whole community of weirdo biohackers that have done this stuff, and I think one of the early use cases was storing, private crypto wallet keys and whatever. I dabbled in that a bit and had some fun with it.
You have some Bitcoin implanted in your body somewhere. You can't tell where. Yeah.
Yeah. Actually, yeah. It was, the modern day equivalent of finding change in the sofa cushions. After I put some orphan crypto on there that I thought was worthless and forgot about it for a few years, went back and found that some community of people loved it and had propped up the value of it. And so it had gone up 50-fold. Wow. So there was a lot of change in those cushions.
That's hilarious.
But the primary use case is mostly as a tech demonstrator. It has my business card on it. You can scan that in by touching it to your phone. It opens the front door to my house. Whatever, simple stuff.
But it's a cool step. It's a cool leap to implant something in your body. I mean, it's a similar leap to a Neuralink. Because for a lot of people, that kind of notion of putting something inside your body, something electronic inside a biological system, is a big leap.
Yeah, we have a kind of a mysticism around the barrier of our skin. We're completely fine with knee replacements, hip replacements, dental implants. But there's a mysticism still around the inviolable barrier that the skull represents. And I think that needs to be treated like any other pragmatic barrier. The question isn't how incredible is it to open the skull? The question is, what benefit can we provide?
So from all the surgeries you've done, from everything you understand the brain, how much does neuroplasticity come into play? How adaptable is the brain? For example, just even in the case of healing from surgery or adapting to the post-surgery situation?
The answer that is sad for me and other people of my demographic is that, plasticity decreases with age, healing decreases with age. Yeah. I have too much gray hair to be optimistic about that. There are theoretical ways to increase plasticity using electrical stimulation. Nothing that is, totally proven out as a robust enough mechanism to offer widely to people. But I think there's cause for optimism that we might find something useful in terms of, say, an implanted electrode that improves learning. Certainly there's been some really amazing work recently from Nicholas Schiff, Jonathan Baker, and others who have a cohort of patients with moderate traumatic brain injury who have had electrodes placed in the deep nucleus in the brain called the centromedian nucleus, or just near the centromedian nucleus. And when they apply small amounts of electricity to that part of the brain, it's almost like electronic caffeine. They're able to improve people's attention and focus. They're able to improve how well people can perform a task. I think in one case, someone who was unable to work after the device was turned on, they were able to get a job. And that's sort of one of the holy grails for me with Neuralink and other technologies like this is, from a purely utilitarian standpoint, can we make people able to take care of themselves and their families economically again? Can we make it so someone who's fully dependent and even maybe requires a lot of caregiver resources, can we put them in a position to be fully independent, taking care of themselves, giving back to their communities? I think that's a very compelling proposition, and what motivates a lot of what I do and what a lot of the people at Neuralink are working for.
It's just a cool possibility that if you put a Neuralink in there, that the brain adapts, like the other part of the brain adapts too.
Yeah.
And integrates it. The capacity of the brain to do that is really interesting. Probably unknown to the degree to which it can do that. But you're now connecting an external thing to it, especially once it's doing stimulation. Like the biological brain and the electronic brain outside of it working together, like the possibilities there are really interesting.
Yeah.
It's still unknown, but interesting. It feels like the brain is really good at adapting to whatever.
Yeah.
But of course, it is a system that by itself is already, like everything serves a purpose. And so you don't want to mess with it too much.
Yeah. It's like, eliminating a species from an ecology. You don't know what the delicate interconnections and dependencies are. The brain is certainly a delicate, complex beast, and we don't know, every potential downstream consequence of a single change that we make.
Do you see yourself doing, so you mentioned P1 surgeries of P2, P3, P4, P5, just more and more humans?
I think, it's a certain kind of brittleness or a failure on the company's side if we need me to do all the surgeries. I think something that I would very much like to work towards is a process that is so simple and so robust on the surgery side that literally anyone could do it. We want to get away from requiring intense expertise or intense experience to have this successfully done and make it as simple and translatable as possible. I mean, I would love it if every neurosurgeon on the planet had no problem doing this. I think we're probably far from a regulatory environment that would allow people that aren't neurosurgeons to do this, but not impossible.
All right, I'll sign up for that. Did you ever anthropomorphize the robot R1? Like, do you give it a name? Do you see it as like a friend that's like working together with you?
I mean, to a certain degree, it's
or an enemy who's going to take the job.
To a certain degree, it's a complex relationship.
All the good relationships are.
It's funny when in the middle of the surgery, there's a part of it where I stand basically shoulder to shoulder with the robot. And so, if you're in the room reading the body language, it's my brother in arms there. We're working together on the same problem. Yeah, I'm not threatened by it.
Keep telling yourself that. Yeah. How have all the surgeries that you've done over the years, the people you've helped, and the stakes, the high stakes that you've mentioned, how has that changed your understanding of life and death?
Yeah. It gives you a very visceral sense, and this may sound trite, but it gives you a very visceral sense that death is inevitable. On one hand, you are, as a neurosurgeon, you're deeply involved in these like just hard to fathom tragedies. Young parents dying, leaving, a 4-year-old behind, say. And on the other hand, it takes the sting out of it a bit because you see how just mind-numbingly universal death is. There's zero chance that I'm going to avoid it. I know, techno optimists right now and longevity buffs right now would disagree on that 0.000% estimate. But I don't see any chance that our generation is going to avoid it. Entropy is a powerful force, and we are very ornate, delicate, brittle DNA machines that aren't up to the cosmic ray bombardment that we're subjected to. So on the one hand, every human that has ever lived died or will die. On the other hand, it's just one of the hardest things to imagine inflicting on anyone that you love is having them gone. I mean, I'm sure you've had friends that aren't living anymore, and it's hard to even think about them. And so I wish I had, arrived at the point of nirvana where, death doesn't have a sting. I'm not worried about it, but I can at least say that I'm comfortable with the certainty of it. If not having found out how to take the tragedy out of it when I think about, my kids, either not having me or me not having them or my wife.
Maybe I've come to accept the intellectual certainty of it, but it may be the pain that comes with losing the people you love. I don't think I've come to understand the existential aspect of it, like that this is going to end. And I don't mean like in some trite way. I mean like it certainly feels like it's not going to end. Like you live life like it's not going to end.
Right.
And the fact that this light that's shining, this consciousness is going to no longer be in one moment, maybe today. It's like it fills me when I really am able to load all that in with Ernest Becker's terror. Like it's a real fear. I think people aren't always honest with how terrifying it is.
Yeah.
I think the more you are able to really think through it, the more terrifying it is. It's not such a simple thing. Oh, well, it's the way life is. And if you really can load that in, it's hard. But I think that's why the Stoics did it, because it like helps you get your shit together and be like this. Well, like the moment, every single moment you're alive is just beautiful.
Yeah.
And it's terrifying that it's gonna end. And it's like you're like almost like you're shivering in the cold, a child, helpless, this kind of feeling.
Yeah.
And then it makes you, when you have warmth, when you have the safety, when you have the love, to really appreciate it. I feel like sometimes in your position, when you mentioned armor, just to see death, it might make you not be able to see that, the finiteness of life, because if you kept looking at that, it might break you. So it's good to know that you're kind of still struggling with that. There's the neurosurgeon, and then there's a human.
Yeah.
And the human is still able to struggle with that and feel the fear of that and the pain of that.
Yeah, it definitely makes you ask the question of how many of these can you see, and not say I can't do this anymore. But I mean, you said it well. I think it gives you an opportunity to just appreciate that you're alive today. And I've got 3 kids and an amazing wife, and I'm really happy. Things are good. I get to help on a project that I think matters. I think it moves us forward. I'm a very lucky person.
It's the early steps of a potentially gigantic leap for humanity. It's a really interesting one. And it's cool because like you read about all this stuff in history where it's like the early days. I've been reading, before going to the Amazon, I would read about explorers that would go and explore even the Amazon jungle for the first time. It's just, those are the early steps.
Yeah.
Or early steps into space, early steps in any discipline, in physics and mathematics. And it's cool because this is like on the grand scale, these are the early steps into delving deep into the human brain. So not just observing the brain, but be able to interact with the human brain.
Yeah.
It's going to help a lot of people, but it also might help us understand what the hell's going on in there.
Yeah. I think ultimately we want to give people more levers that they can pull, right? Like you want to give people options. If you can give someone a dial that they can turn on how happy they are, I think that makes people really uncomfortable. But now talk about major depressive disorder, talk about people that are committing suicide at an alarming rate in this country, and try to justify that queasiness in that light of you can give people a knob to take away suicidal ideation, suicidal intention. I would give them that knob. I don't know how you justify not doing that.
Yeah, you can think about like all the suffering that's going on in the world. Like every single human being that's suffering right now, it's like it'd be a glowing red dot. The more suffering, the more it's glowing, and you just see the map of human suffering. And any technology that allows you to dim that light of suffering on a grand scale is pretty exciting, because there's a lot of people suffering, and most of them suffer quietly. Yeah. And we turn we look away too often, and we should remember those that are suffering, because once again, most of them are suffering quietly.
Well, and on a grander scale, the fabric of society. People have a lot of complaints about how our social fabric is working or not working, how our politics is working or not working. Those things are made of neurochemistry too, in aggregate, right? Like our politics is composed of individuals with human brains, and the way it works or doesn't work is potentially tunable, in the sense that, I don't know, say, remove our addictive behaviors or tune our addictive behaviors for social media, or our addiction to outrage, our addiction to sharing the most angry political tweet we can find. I don't think that leads to a functional society. And if you had options for people to moderate that maladaptive behavior, there could be huge benefits to society. Maybe we could all work together a little more harmoniously toward useful ends.
There's a sweet spot, like you mentioned. You don't want to completely remove all the dark sides of human nature, because those kind of are somehow necessary to make the whole thing work. But there's a sweet spot.
Yeah, I agree. You gotta suffer a little, just not so much that you lose hope.
Yeah. When all the surgeries you've done, have you seen consciousness in there ever? Was there like a glowing light?
I have this sense that I never found it. Okay. Never removed it, like a Dementor in Harry Potter. I have this sense that consciousness is a lot less magical than our instincts want to claim it is. It seems to me like a useful analog for thinking about what consciousness is in the brain. Is that we have a really good intuitive understanding of what it means to, say, touch your skin and know what's being touched. I think consciousness is just that level of sensory mapping applied to the thought processes in the brain itself. So what I'm saying is, consciousness is the sensation of some part of your brain being active. So you feel it working. You feel the part of your brain that thinks of red things or winged creatures or the taste of coffee. You feel those parts of your brain being active the way that I'm feeling my palm being touched, right? And that sensory system that feels the brain working is consciousness.
That's so brilliant. It's the same way, it's the sensation of touch when you're touching a thing. Consciousness is the sensation of you feeling your brain working, your brain thinking, your brain perceiving.
Which isn't which isn't like a warping of space-time or some quantum field effect, right? It's nothing magical. People always want to ascribe to consciousness something truly different. And there's this awesome long history of people looking at whatever the latest discovery in physics is to explain consciousness, because it's the most magical, the most out there thing that you can think of. And people always, want to do that with consciousness. I don't think that's necessary. It's just a very useful and gratifying way of feeling your brain work.
And as we said, it's one heck of a brain.
Yeah.
Everything we see around us, everything we love, everything that's beautiful came from brains like these.
It's all electrical activity happening inside your skull.
And I, for one, am grateful that there's people like you that are exploring all the ways that it works and all the ways it can be made better.
Thanks,
Matthew,
Lex.
thank you so much for talking today.
It's been a joy.
Thanks for listening to this conversation with Matthew McDougall. And now, dear friends, here's Bliss Chapman, Brain Interface Software Lead at Neuralink. You told me that you've met hundreds of people with spinal cord injuries or with ALS, and that your motivation for helping at Neuralink is grounded in wanting to help them. Can you describe this motivation?
Yeah. First, just a thank you to all the people I've gotten a chance to speak with for sharing their stories with me. I don't think there's any world really in which I can share their stories in as powerful a way as they can. But just I think to summarize at a very high level, what I hear over and over again is that people with ALS or severe spinal cord injury in a place where they basically can't move physically anymore, really at the end of the day are looking for independence. And that can mean different things for different people. For some folks, it can mean the ability just to be able to communicate again independently without needing to wear something on their face, without needing a caretaker to be able to put something in their mouth. For some folks, it can mean independence to be able to work again, to be able to navigate a computer digitally efficiently enough to be able to get a job, to be able to support themselves, to be able to move out and ultimately be able to support themselves after their family maybe isn't there anymore to take care of them. And for some folks, it's as simple as just being able to respond to their kid in time before they, run away or get interested in something else. And these are deeply personal and sort of very human problems. And what strikes me again and again when talking with these folks is that this is actually an engineering problem. This is a problem that with the right resources, with the right team, we can make a lot of progress on. And at the end of the day, I think that's a deeply inspiring message and something that makes me excited to get up every day.
So it's both an engineering problem in terms of a BCI, for example, that can give them capabilities where they can interact with the world. But also on the other side, it's an engineering problem for the rest of the world to make it more accessible for people living with quadriplegia.
Yeah. And actually, I'll take a broad view sort of lens on this for a second. I think I'm very in favor of anyone working in this problem space. So beyond BCI, I'm happy and excited and willing to support any way I can folks working on eye tracking systems, working on speech to text systems, working on head trackers or mouse sticks or quad sticks. And I've met many engineers and folks in the community that do exactly those things. And I think for the people we're trying to help, it doesn't matter what the complexity of the solution is as long as the problem is solved. And I want to emphasize that there can be many solutions out there that can help with these problems. And BCI is one of a collection of such solutions. So BCI in particular, I think, offers several advantages here. And I think the folks that recognize this immediately are usually the people who have spinal cord injury or some form of paralysis. Usually you don't have to explain to them why this might be something that could be helpful. It's usually pretty self-evident. But for the rest of us, folks that don't live with severe spinal cord injury or who don't know somebody with ALS, it's not often obvious why you would want a brain implant to be able to connect and navigate a computer. And it's surprisingly nuanced to the degree that I've learned a huge amount just working with Noland in the first Neuralink clinical trial and understanding from him in his words why this device is impactful for him. And it's a nuanced topic. It can be the case that even if he can achieve the same thing, for example, with a mouse stick when navigating a computer, he doesn't have access to that mouse stick every single minute of the day. He only has access when someone is available to put it in front of him. And so a BCI can really offer a level of independence and autonomy that if it wasn't literally physically part of your body, it would be hard to achieve in any other way.
So there's a lot of fascinating aspects to what it takes to get Nolan to be able to control a cursor on the screen with his mind. You texted me something that I just love. You said, I was part of the team that interviewed and selected P1. I was in the operating room during the first human surgery, monitoring live signals coming out of the brain. I work with the user basically every day to develop new UX paradigms, decoding strategies, and I was part of the team that figured out how to recover useful BCI to new world record levels when the signal quality degraded. We'll talk about, I think, every aspect of that, but just zooming out, what was it like to be part of that, part of that team, and part of that historic, I would say, historic first?
Yeah, I think for me, this is something I've been excited about for close to 10 years now. And so to be able to be even just some small part of making it a reality is extremely exciting. A couple maybe special moments during that whole process that I'll never really truly forget. One of them is during the actual surgery. At that point in time, I know Nolan quite well. I know his family. And so I think the initial reaction when Nolan is rolled into the operating room is just a, oh shit kind of reaction. But at that point, muscle memory kicks in and you sort of go into, you let your body just do all the talking. And I have the lucky job in that particular procedure to just be in charge of monitoring the implant. So my job is to sit there, to look at the signals coming off the implant, to look at the live brain data streaming off the device as threads are being inserted into the brain, and just to basically observe and make sure that nothing is going wrong, or that there's no red flags or fault conditions that we need to go and investigate or pause the surgery to debug. And because I had that sort of spectator view of the surgery, I had a slightly removed perspective than I think most folks in the room. I got to sit there and think to myself, wow, that brain is moving a lot. When you look inside the little craniectomy that we stick the threads in, one thing that most people don't realize is the brain moves. The brain moves a lot when you breathe, when your heart beats, and you can see it visibly. So, that's something that I think was a surprise to me and very, very exciting to be able to see someone's brain who you physically know and have talked with at length actually pulsing and moving inside their skull.
And they used that brain to talk to you previously. Yes. And now it's right there moving.
Yep.
Actually, I didn't realize that in terms of the thread sending. So the Neuralink implant is active during surgery. So, and one thread at a time, you're able to start seeing the signal.
Yeah.
So that's part of the way you test that the thing is working.
Yeah. So actually, in the operating room, right after we sort of finished all the thread insertions, I started collecting what's called broadband data. So broadband is basically the most raw form of signal you can collect from a Neuralink electrode. It's essentially a measurement of the local field potential, or the voltage essentially measured by that electrode. And we have a certain mode in our application that allows us to visualize where detected spikes are. So it visualizes sort of where in the broadband signal, in its very, very raw form of the data, a neuron is actually spiking. And so one of these moments that I'll never forget as part of this whole clinical trial is seeing live in the operating room, while he's still under anesthesia, beautiful spikes being shown in the application, just streaming live to a device I'm holding in my hand.
So this is no signal processing, the raw data, and then the signals processing is on top of it. You're seeing the spikes detected.
Right, yeah.
And that's a UX too.
Yes.
That looks beautiful as well.
During that procedure, there was actually a lot of cameramen in the room, so they also were curious and wanted to see. There's several neurosurgeons in the room who are all just excited to see robots taking their job. And they're all, crowded around a small little iPhone watching this live brain data stream out of his brain.
What was that like, seeing the robot do some of the surgery? So the computer vision aspect where it detects all the spots that avoid the blood vessels, and then obviously with human supervision, then actually doing the really high precision connection of the threads to the brain.
Yeah, it's a good question. My answer is going to be pretty lame here, but it was boring.
Yeah.
I've seen it so many times. Yeah, that's exactly how you want surgery to be. You want it to be boring.
Yeah.
Because I've seen it so many times. I've seen the robot do this surgery literally hundreds of times. And so it was just one more time.
Yeah, all the practice surgeries and the proxies. And this is just another day.
Yeah.
So what about when Nolan woke up? Well, do you remember a moment where he was able to move the cursor, not move the cursor, but get signal from the brain such that it was able to show that there's a connection?
Yeah. Yeah. So we are quite excited to move as quickly as we can. And Nolan was really, really excited to get started. He wanted to get started actually the day of surgery. But we waited till the next morning, very patiently. It's a long night. And the next morning in the ICU, where he was recovering, he wanted to get started and actually start to understand what kind of signal we can measure from his brain. And maybe for folks who are not familiar with the Neuralink system, we implant the Neuralink system or the Neuralink implant in the motor cortex. So the motor cortex is responsible for representing things like motor intent. So if you imagine closing and opening your hand, that kind of signal representation would be present in the motor cortex. If you imagine moving your arm back and forth or wiggling a pinky, this sort of signal can be present in the motor cortex. So one of the ways we start to sort of map out what kind of signal do we actually have access to in any particular individual's brain is through this task called body mapping. And body mapping is where you essentially present a visual to the user and you say, hey, imagine doing this. And the visual is, a 3D hand opening and closing or index finger modulating up and down. And you ask the user to imagine that. And obviously you can't see them do this because they're paralyzed. So you can't see them actually move their arm. But while they do this task, you can record neural activity. And you can basically offline model and check, can I predict or can I detect the modulation corresponding with those different actions? And so we did that task and we realized, hey, there's actually some modulation associated with some of his hand motion, which was the first indication that, okay, we can potentially use that modulation to do useful things in the world. For example, control a computer cursor. And he started playing with it, the first time we showed him it. And we actually just took the same live view of his brain activity and put it in front of him. And we said, hey, you tell us what's going on. Mm-hmm. We're not you. You're able to imagine different things. And we know that it's modulating some of these neurons. So you figure out for us what that is actually representing. And so he played with it for a bit. He was like, I don't quite get it yet. He played for a bit longer. And he said, oh, when I move this finger, I see this particular neuron start to fire more. And I said, okay, prove it. Do it again. And so he said, okay, 3, 2, 1, boom. Mm-hmm. And the minute he moved, you can see like instantaneously, this neuron is firing. Single neuron, I can tell you the exact channel number if you're interested. It's stuck in my brain now forever. But that single channel firing was a beautiful indication that it was behaviorally modulated neural activity that could then be used for downstream tasks like decoding a computer cursor.
And when you say single channel, is that associated with a single electrode?
Yeah, so channel and electrode are interchangeable.
And there's 1,024 of those.
1,024, yeah.
It's incredible that works. That really, when I was learning about all this and like loading it in, it was just blowing my mind that the intention, you can visualize yourself moving the finger, that can turn into a signal. And the fact that you can then skip that step and visualize the cursor moving or have the intention of the cursor moving and that leading to a signal that can then be used to move the cursor. There is so many exciting things there to learn about the brain, about the way the brain works. The very fact of their existing signal that can be used is really powerful.
Yep.
But it feels like that's just like the beginning of figuring out how that signal can be used really, really effectively. I should also just, there's so many fascinating details here, but you mentioned the body mapping step. At least in the version I saw that Nolan was showing off, there's like a super nice interface, like a graphical interface. Yeah. Like, it just felt like I was like in the future because it like, I guess it visualizes you moving the hand. Yep. And there's a very like a sexy polished interface that hello. Yeah. I don't know if there's a voice component, but it just felt like it's like when you wake up in a really nice video game and this is a tutorial at the beginning of that video game. Yeah. This is what you're supposed to do. It's cool.
No, I mean, the future should feel like the future.
But it's not easy to pull that off. I mean, it needs to be simple, but not too simple.
Yeah, and I think the UX design component here is underrated for BCI development in general. There's a whole interaction effect between the ways in which you visualize an instruction to the user and the kinds of signal you can get back. And that quality of sort of your behavioral alignment to the neural signal is a function of how good you are at expressing to the user what you want them to do. And so, yeah, we spend a lot of time thinking about the UX, of how we build our applications, of how the decoder actually functions, the control surfaces it provides to the user. All these little details matter a lot.
So maybe it'd be nice to get into a little bit more detail of what the signal looks like and what the decoding looks like. Yeah. So there's a N1 implant that has, like we mentioned, 1,024 electrodes, and that's collecting raw data, raw signal. What does that signal look like? And what are the different steps along the way before it's transmitted, and what is transmitted, all that kind of stuff.
Yeah. This is going to be a fun one.
Let's go.
Maybe before diving into what we do, it's worth understanding what we're trying to measure, because that dictates a lot of the requirements for the system that we build. And what we're trying to measure is really individual neurons producing action potentials. An action potential is, you can think of it like a little electrical impulse that you can detect if you're close enough. And by being close enough, I mean like within, let's say, 100 microns of that cell. And 100 microns is a very, very tiny distance. And so the number of neurons that you're going to pick up with any given electrode is just a small radius around that electrode.
Mm-hmm.
And the other thing worth understanding about the underlying biology here is that when neurons produce an action potential, the width of that action potential is about 1 millisecond. So from the start of the spike to the end of the spike, that whole width of that sort of characteristic feature of a neuron firing is 1 millisecond wide. And if you want to detect that an individual spike is occurring or not, you need to sample that signal or sample the local field potential nearby that neuron much more frequently than once a millisecond. You need to sample many, many times per millisecond to be able to detect that this is actually the characteristic waveform of a neuron producing an action potential.
Mm-hmm.
And so we sample across all 1,024 electrodes about 20,000 times a second. 20,000 times a second means for every given 1 millisecond window, we have about 20 samples that tell us what that exact shape of that action potential looks like.
Mm-hmm.
And once we've sort of sampled at super high rate the underlying electrical field nearby these cells, we can process that signal into just where do we detect a spike or where do we not? Sort of a binary signal, 1 or 0. Do we detect a spike in this 1 millisecond or not? And we do that because the actual information carrying sort of subspace of neural activity is just when are spikes occurring.
Mm-hmm.
Essentially, everything that we care about for decoding can be captured or represented in the frequency characteristics of spike trains, meaning how often are spikes firing in any given window of time. And so that allows us to do sort of a crazy amount of compression from this very rich, high density, signal to something that's much, much more sparse and compressible that can be sent out over a wireless radio, like a Bluetooth communication, for example.
Quick tangents here. You mentioned electrode, neuron. There's a local neighborhood of neurons nearby. How difficult is it to isolate from where the spike came from?
Yeah, so there's a whole field of sort of academic neuroscience work on exactly this problem of basically given a single electrode or given a set of electrodes measuring a set of neurons, how can you sort of spike sort
Mm-hmm.
which spikes are coming from what neuron? And this is a problem that's pursued in academic work because you care about it for understanding what's going on in the underlying sort of neuroscience of the brain. If you care about understanding how the brain's representing information, how that's evolving through time, then that's a very, very important question to understand. For sort of the engineering side of things, at least at the current scale, if the number of neurons per electrode is relatively small, you can get away with basically ignoring that problem completely. You can think of it like sort of a random projection of neurons to electrodes. And there may be, in some cases, more than one neuron per electrode. But if that number is small enough, those signals can be thought of as sort of a union of the two.
Mm-hmm.
And for many applications, that's a totally reasonable trade-off to make and can simplify the problem a lot. And as you sort of scale out channel count, the relevance of distinguishing individual neurons becomes less important because you have more overall signal and you can start to rely on sort of correlations or covariance structure in the data to help understand when that channel is firing, what does that actually represent? Because you know that when that channel is firing in concert with these other 50 channels, that means move left. But when that same channel is firing with concert with these other 10 channels, that means move right.
Okay, so you have to do this kind of spike detection on board. And you have to do that super efficiently, so fast and not use too much power because you don't want to be generating too much heat. So it have to be a super simple signal processing step.
Yeah.
Is there some wisdom you can share about what it takes to overcome that challenge?
Yeah. So we've tried many different versions of basically turning this raw signal into sort of a feature that you might want to send off the device. And I'll say that I don't think we're at the final step of this process. This is a long journey. We have something that works clearly today, but there can be many approaches that we find in the future that are much better than what we do right now. So some versions of what we do right now, and there's a lot of academic heritage to these ideas, so I don't want to claim that these are original Neuralink ideas or anything like that. But one of these ideas is basically to build a sort of like a convolutional filter almost, if you will, that slides across the signal and looks for a certain template to be matched. And that template consists of sort of how deep the spike modulates, how much it recovers, and what the duration and window of time is that the whole process takes. And if you can see in the signal that that template is matched within certain bounds, then you can say, okay, that's a spike. One reason that approach is super convenient is that you can actually implement that extremely efficiently in hardware, which means that you can run it in low power across 1,024 channels all at once. Another approach that we've recently started exploring, and this can be combined with the spike detection approach, is something called spike band power. And the benefits of that approach are that you may be able to pick up some signal from neurons that are maybe too far away to be detected as a spike, because the farther away you are from an electrode, the weaker that actual spike waveform will look like on that electrode. So you might be able to pick up, population level activity of things that are, maybe slightly outside the normal recording radius, what neuroscientists sometimes refer to as the hash of activity, the other stuff that's going on.
Yeah.
And you can look at sort of across many channels how that sort of background noise is behaving, and you might be able to get more juice out of the signal that way. But it comes at a cost. That signal is now a floating point representation, which means it's more expensive to send out over power. It means you have to find different ways to compress it that are different than what you can apply to binary signals. So there's a lot of different challenges associated with these different modalities.
So also in terms of communication, you're limited by the amount of data you can send.
Yeah.
So, and also because you're currently using the Bluetooth protocol, you have to batch stuff together. But you have to also do this keeping the latency crazy low, like crazy low. Anything to say about the latency?
Yeah, this is a passion project of mine. So I want to build the best mouse in the world.
Yeah.
I don't want to build like the Chevrolet Spark or whatever of electric cars. I want to build like the Tesla Roadster version of a mouse. And I really do think it's quite possible that within 5 to 10 years that most esports competitions are dominated by people with paralysis. This is like a very real possibility for a number of reasons. One is that they'll have access to the best technology to play video games effectively. The second is they have the time to do so. So those two factors together are particularly potent for esport competitors.
Unless people without paralysis are also allowed to implant Neuralink,
right?
Which is another way to interact with a digital device. Mm-hmm. And there's something to that. If it's a fundamentally different experience, more efficient experience, even if it's not like some kind of full-on high bandwidth communication, if it's just the ability to move the mouse 10x faster, like the bits per second, if I can achieve a bits per second at 10x what I can do with the mouse, that's a really interesting possibility of what they can do, especially as you get really good at it with training.
It's definitely the case that you have a higher ceiling of performance, because you don't have to buffer your intention through your arm, through your muscle. You get, just by nature of having a brain implant at all, like 75 millisecond lead time on any action that you're actually trying to take. And there's some nuance to this, like there's evidence that the motor cortex, you can sort of plan out sequences of actions, so you may not get that whole benefit all the time. But for sort of like reaction time style games where you just want to, somebody's over here, snipe them, that kind of thing, you actually do have just an inherent advantage because you don't need to go through muscle. So the question is just how much faster can you make it? And we're already, faster than what you would do if you're going through muscle from a latency point of view. And we're in the early stages of that. I think we can push it. Sort of our end-to-end latency right now from brain spike to cursor movement is about 22 milliseconds. If you think about the best mice in the world, the best gaming mice, that's about 5 milliseconds-ish of latency, depending on how you measure, depending how fast your screen refreshes. There's a lot of characteristics that matter there. But yeah, and the rough time for like a neuron in the brain to actually impact your command of your hand is about 75 milliseconds. So if you look at those numbers, you can see that we're already competitive and slightly faster than what you'd get by actually moving your hand. And this is something that, if you ask Nolan about it, when he moved the cursor for the first time, we asked him about this. It was something I was super curious about. Like, what does it feel like when you're modulating, a click intention, or when you're trying to just move the cursor to the right? He said it moves before he is like actually intending it to, which is kind of a surreal thing and something that, I would love to experience myself one day. What is that like to have the thing just be so immediate, so fluid that it feels like it's happening before you're actually intending it to move?
Yeah, I suppose we've gotten used to that latency, that natural latency that happens. So is currently the bottleneck the communication? So like the Bluetooth communication, what's the actual bottleneck? I mean, there's always going to be a bottleneck, but what's the current bottleneck?
Yeah, a couple things. So kind of hilariously, Bluetooth low energy protocol has some restrictions on how fast you can communicate. So the protocol itself establishes a standard of, the most frequent sort of updates you can send are on the order of 7.5 milliseconds. And as we push latency down to the level of sort of individual spikes impacting control, that level of resolution, that kind of protocol is going to become a limiting factor at some scale. Another sort of important nuance to this is that it's not just the Neuralink itself that's part of this equation. If you start pushing latency sort of below the level of how fast screens refresh, then you have another problem. Like, you need your whole system to be able to be as reactive as the sort of limits of what the technology can offer.
Yes.
Like, you need the screen, like 120 hertz just doesn't, work anymore if you're trying to have something respond at something that's, at the level of 1 millisecond.
That's a really cool challenge. I also like that for a t-shirt, the best mouse in the world. Tell me on the receiving end, so the decoding step. Now we figured out what the spikes are. We got them all together. Now we're sending that over to the app. What's the decoding step look like?
Yeah. So maybe first, what is decoding? I think there's probably a lot of folks listening that just have no clue what it means to decode brain activity.
Actually, even if we zoom out beyond that, what is the app? So there's an implant that's wirelessly communicating with any digital device that has an app installed.
Yep.
So maybe can you tell me at high level what the app is, what the software is outside of the brain?
Yeah. So maybe working backwards from the goal. The goal is to help someone with paralysis, in this case, Nolan, be able to navigate his computer independently. And we think the best way to do that is to offer them the same tools that we have to navigate our software, because we don't want to have to rebuild an entire software ecosystem for the brain, at least not yet. Maybe someday you can imagine there's UXs that are built natively for BCI, but in terms of what's useful for people today, I think most people would prefer to be able to just control mouse and keyboard inputs to all the applications that they want to use for their daily jobs, for communicating with their friends, etc. And so the job of the application is really to translate this wireless stream of brain data coming off the implant into control of the computer. And we do that by essentially building a mapping from brain activity to sort of the HID inputs to the actual hardware. So HID is just the protocol for communicating like input device events. So for example, move mouse to this position or press this key down. And so that mapping is fundamentally what the app is responsible for. But there's a lot of nuance of how that mapping works that we spent a lot of time to try to get right. And we're still in the early stages of a long journey to figure out how to do that optimally. So one part of that process is decoding. So decoding is this process of taking the statistical patterns of brain data that's being channeled across this Bluetooth connection to the application and turning it into, for example, a mouse movement. And that decoding step, you can think of it in a couple different parts. So similar to any machine learning problem, there's a training step and there's an inference step. The training step in our case is a very intricate behavioral process where the user has to imagine doing different actions. So for example, they'll be presented a screen with a cursor on it, and they'll be asked to push that cursor to the right. Then imagine pushing that cursor to the left, push it up, push it down. And we can basically build up a pattern, or using any sort of modern ML method, a mapping of given this brain data and that imagined behavior, map one to the other. And then at test time, you take that same pattern matching system, in our case, it's a deep neural network, and you run it, and you take the live stream of brain data coming off their implant, you decode it by pattern matching to what you saw at calibration time, and you use that for control of the computer. Now, a couple like sort of rabbit holes that I think are quite interesting. One of them has to do with how you build that best template matching system, because there's a variety of behavioral challenges and also debugging challenges when you're working with someone who's paralyzed. Because again, fundamentally, you don't observe what they're trying to do. You can't see them attempt to move their hand. And so you have to figure out a way to instruct the user to do something and validate that they're doing it correctly, such that then you can downstream build with confidence the mapping between the neural spikes and the intended action. And by doing the action correctly, what I really mean is at the level of resolution of what neurons are doing. So if in an ideal world, you could get a signal of behavioral intent that is ground truth accurate at the scale of sort of 1 millisecond resolution, then with high confidence, I could build a mapping from my neural spikes to that behavioral intention. But the challenge is, again, that you don't observe what they're actually doing. And so there's a lot of nuance to how you build user experiences that give you more than just sort of a coarse, on average, correct representation of what the user's intending to do. If you want to build the world's best mouse, you really want it to be as responsive as possible. You want it to be able to do exactly what the user's intending at every sort of step along the way, not just on average be correct when you're trying to move it from left to right. And building a behavioral sort of calibration game or sort of software experience that gives you that level of resolution is what we spend a lot of time working on.
So the calibration process the interface has to encourage precision, meaning like whatever it does, it should be super intuitive, that the next thing the human is going to likely do is exactly that intention that you need, and only that intention.
Yeah.
And you don't have any feedback except that may be speaking to you afterwards, what they actually did. You can't, oh yeah.
Right.
So that's fundamentally, that is a really exciting UX challenge, because that's all on the UX. It's not just about being friendly or nice or usable.
Yeah.
It's like
User experience is how it works.
it's how it works.
Yeah.
For the calibration, and calibration, at least at this stage of Neuralink, is like fundamental to the operation of the thing. And not just calibration, but continued calibration, essentially.
Yeah. And maybe you said something that I think is worth exploring there a little bit. You said it's, primarily a UX challenge. And I think a large component of it is, but there is also a very interesting machine learning challenge here, which is given some, data set, including some on average correct behavior of asking the user to move up or move down, move right, move left. And given a data set of neural spikes, is there a way to infer in some kind of semi-supervised or entirely unsupervised way what that high resolution version of their intention is? And if you think about it, like there probably is, because there are enough data points in the data set, enough constraints on your model, that there should be a way with the right sort of formulation to let the model figure out itself. For example, at this millisecond, this is exactly how hard they're pushing upwards. And at this millisecond, this is how hard they're trying to push upwards.
It's really important to have very clean labels. Yes. So like the problem becomes much harder from the machine learning perspective if the labels are noisy.
That's correct.
And then to get the clean labels, that's a UX challenge.
Correct. Although clean labels, I think maybe it's worth exploring what that exactly means. I think any given labeling strategy will have some number of assumptions it makes about what the user is attempting to do. Those assumptions can be formulated in a loss function, or they can be formulated in terms of heuristics that you might use to just try to estimate or guesstimate what the user is trying to do. And what really matters is how accurate are those assumptions. For example, you might say, hey, user, push upwards and follow the speed of this cursor. And your heuristic might be that they're trying to do it exactly what that cursor is trying to do. Another competing heuristic might be they're actually trying to go slightly faster at the beginning of the movement and slightly slower at the end. And those competing heuristics may or may not be accurate reflections of what the user is trying to do. Another version of the task might be, hey, user, imagine moving this cursor a fixed offset. So rather than follow the cursor, just try to move it exactly 200 pixels to the right. So here's the cursor, here's the target. Okay, cursor disappears. Try to move that now invisible cursor 200 pixels to the right. And the assumption in that case would be that the user can actually modulate correctly that position offset. But that position offset assumption might be a weaker assumption, and therefore potentially you can make it more accurate than these heuristics that are trying to guesstimate at each millisecond what the user is trying to do. So you can imagine different tasks that make different assumptions about the nature of the user intention, and those assumptions being correct is what I would think of as a clean label.
For that step, what are we supposed to be visualizing? There's a cursor, and you want to move that cursor to the right, the left, up and down, or maybe move them by a certain offset. So that's one way. Is that the best way to do calibration? So for example, an alternative crazy way that probably is playing a role here is a game like WebGrid, where you're just getting a very large amount of data, the person playing a game, where if they are in a state of flow, maybe you can get clean signal as a side effect.
Yep.
Is that not an effective way for initial calibration?
Yeah, great question. There's a lot to unpack there. So the first thing I would draw a distinction between is sort of open loop versus closed loop. So open loop, what I mean by that is the user is sort of going from 0 to 1. They have no model at all, and they're trying to get to the place where they have some level of control at all. In that setup, you really need to have some task that gives the user a hint of what you want them to do, such that you can build its mapping again from brain data to output. Then once they have a model, you could imagine them using that model and actually adapting to it and figuring out the right way to use it themselves, and then retraining on that data to give you sort of a boost in performance. There's a lot of challenges associated with both of these techniques, and we can sort of rabbit hole into both of them if you're interested. But the sort of challenge with the open loop task is that the user themselves doesn't get proprioceptive feedback about what they're doing. They don't, necessarily perceive themselves or feel, the mouse under their hand when they're using an open loop, or when they're trying to do an open loop calibration. They're being asked to perform something like, imagine if you sort of had your whole right arm numbed and you stuck it in a box and you couldn't see it. So you had no visual feedback and you had no proprioceptive feedback about what the position or activity of your arm was. And now you're asked, okay, given this thing on the screen that's moving from left to right, match that speed. And you basically can try your best to, invoke whatever that imagined action is in your brain that's moving the cursor from left to right. But in any situation, you're going to be inaccurate and maybe inconsistent in how you do that task. And so that's sort of the fundamental challenge of open loop. The challenge with closed loop is that once the user's given a model and they're able to start moving the mouse on their own, they're going to very naturally adapt to that model. And that co-adaptation between the model learning what they're doing and the user learning how to use the model may not find you the best sort of global minima. It may be that your first model was noisy in some ways, or maybe just had some quirk. There's some part of the data distribution it didn't cover super well. And the user now figures out, because they're a brilliant user like Nolan, they figure out the right sequence of imagined motions or the right angle they have to hold their hand at to get it to work. And they'll get it to work great. But then the next day they come back to their device and maybe they don't remember exactly all the tricks that they used the previous day. And so there's a complicated sort of feedback cycle here that can emerge and can make it a very, very difficult debugging process.
Okay, there's a lot of really fascinating things there. Actually, just to stay on the closed loop, I've seen situations. This actually happened watching psychology grad students. They use a piece of software when they don't know how to program themselves. They use a piece of software that somebody else wrote, and it has a bunch of bugs. And they figure out and they've been using it for years.
Yeah.
They figure out ways to work around it.
Yeah.
Oh, that just happens. Nobody considers maybe we should fix this. They just adapt. And that's a really interesting notion that we're really good at adapting, but you need to still, that might not be the optimal.
Yeah.
Okay, so how do you solve that problem? Do you have to restart from scratch every once in a while kind of thing?
Yeah, it's a good question. First and foremost, I would say this is not a solved problem. And for anyone who's listening in academia who works on BCIs, I would also say this is not a problem that's solved by simply scaling channel count. So this is, maybe that can help, and you can get sort of richer covariance structures that you can use to exploit when trying to come up with good labeling strategies. But if you're interested in problems that aren't going to be solved inherently by just scaling channel count, this is one of them. Yeah, so how do you solve it? It's not a solved problem. That's the first thing I want to make sure it gets across. The second thing is any solution that involves closed loop is going to become a very difficult debugging problem. And one of my sort of general heuristics for choosing what problems to tackle is that you want to choose the one that's going to be the easiest to debug. Because if you can do that, even if the ceiling is lower, you're going to be able to move faster because you have a tighter iteration loop debugging the problem. And in the open loop setting, there's not a feedback cycle to debug with the user in the loop. And so there's some reason to think that that should be an easier debugging problem. The other thing that's worth understanding is that even in a closed loop setting, there's no special sauce or magic of how to infer what the user is truly attempting to do. In the closed loop setting, although they're moving the cursor on the screen, they may be attempting something different than what your model is outputting. So what the model is outputting is not a signal that you can use to retrain if you want to be able to improve the model further. You still have this very complicated guesstimation or unsupervised problem of figuring out what is the true user intention underlying that signal. And so the open loop problem has the nice property of being easy to debug, and the second nice property of it has all the same information and content as the closed loop scenario. Another thing I want to mention and call out is that this problem doesn't need to be solved in order to give useful control to people. Even today with the solutions we have now and that academia has built up over decades, the level of control that can be given to a user, today is quite useful. It doesn't need to be solved to get to that level of control. But again, I want to build the world's best mouse. I want to make it, so good that it's not even a question that you want it. And to build the world's best mouse, the superhuman version, you really need to nail that problem. And a couple maybe details of previous studies that we've done internally that I think are very interesting to understand when thinking about how to solve this problem. The first is that even when you have ground truth data of what the user is trying to do, and you can get this with an able-bodied monkey, a monkey that has a Neuralink device implanted and moving a mouse to control a computer, even with that ground truth data set, it turns out that the optimal thing to predict to produce high-performance BCI is not just the direct control of the mouse. You could imagine, building a data set of what's going on in the brain and what is the mouse exactly doing on the table. And it turns out that if you build the mapping from neural spikes to predict exactly what the mouse is doing, that model will perform worse than a model that is trained to predict sort of higher level assumptions about what the user might be trying to do. For example, assuming that the monkey is trying to go in a straight line to the target. It turns out that making those assumptions is actually more effective in producing a model than actually predicting the underlying hand movement.
So the intention, not the physical movement or whatever.
Yeah.
There's obviously a really strong correlation between the two, but the intention is a more powerful thing to be chasing.
Right.
Well, that's also super interesting. I mean, the intention itself is fascinating because, yes, with the BCI here in this case, with the digital telepathy, you're acting on the intention, not the action, which is why there's an experience of like feeling like it's happening before you meant for it to happen. That is so cool. And that is why you could achieve like superhuman performance probably in terms of the control of the mouse. So for open loop, just to clarify, so whenever the person is tasked to like move the mouse to the right, you said there's not feedback. So they don't get that satisfaction of like actually getting it to move, right?
So you could imagine giving the user feedback on a screen, but it's difficult because at this point you don't know what they're attempting to do. So what can you show them that would basically give them a signal of I'm doing this correctly or not correctly? So let's take a very specific example. Like maybe your calibration task looks like you're trying to move the cursor a certain position offset. So your instructions to the user are, hey, the cursor's here. Now, when the cursor disappears, imagine moving it 200 pixels from where it was to the right to be over this target. In that kind of scenario, you could imagine coming up with some sort of consistency metric that you could display to the user of, okay, I know what the spike train looks like on average when you do this action to the right. Maybe I can produce some sort of probabilistic estimate of how likely is that to be the action you took given the latest trial or trajectory that you imagined. And that could give the user some sort of feedback of how consistent are they across different trials. You could also imagine that if the user is prompted with that kind of consistency metric, that maybe they just become more behaviorally engaged to begin with because the task is kind of boring when you don't have any feedback at all. And so there may be benefits to the user experience of showing something on the screen, even if it's not accurate, just because it keeps the user motivated to try to increase that number or push it upwards.
So there's a psychology element here.
Yeah, absolutely.
And again, all of that is UX challenge. How much signal drift is there? Hour to hour, day to day, week to week, month to month? How often do you have to recalibrate because of the signal drift?
Yeah. So this is a problem we've worked on both with NHP, non-human primates, before our clinical trial, and then also with Noland during the clinical trial. Maybe the first thing that's worth stating is what the goal is here. So the goal is really to enable the user to have a plug-and-play experience where, I guess they don't have to plug anything in, but a play experience where they can use the device whenever they want to, however they want to. Mm-hmm. And that's really what we're aiming for. And so there can be a set of solutions that get to that state without considering this non-stationarity problem. So maybe the first solution here that's important is that they can recalibrate whenever they want. This is something that that Noland has the ability to do today. So he can recalibrate the system, at 2 a.m. in the middle of the night without his, caretaker or parents or friends around to help push a button for him. The other important part of the solution is that when you have a good model calibrated, that you can continue using that without needing to recalibrate it. So how often he has to do this recalibration today depends really on his appetite for performance. There are, we observe a sort of a degradation through time of how well any individual model works, but this can be mitigated behaviorally by the user adapting their control strategy. It can also be mitigated through a combination of sort of software features that we provide to the user. For example, we let the user adjust exactly how fast the cursor is moving. We call that the gain, for example, the gain of how fast the cursor reacts to any given input intention. They can also adjust the smoothing, how smooth the output of that cursor intention actually is. They can also adjust the friction, which is how easy is it to stop and hold still. And all these software tools allow the user a great deal of flexibility and troubleshooting mechanisms to be able to solve this problem for themselves.
By the way, all of this is done by looking to the right side of the screen, selecting the mixer, and in the mixer you have it's
like DJ mode. DJ mode for your BCI.
So, I mean, it's a really well done interface. It's really, really well done. And so, yeah, there's that bias that there's a cursor drift that Nolan talked about in a stream. Although he said that you guys were just playing around with it with him and they're constantly improving. So that could have been just a snapshot of that particular moment, a particular day. But he said that there was this cursor drift and this bias that could be removed by him, I guess, looking to the right side of the screen or the left side of the screen to kind of adjust the bias.
Yeah.
That's one interface action, I guess, to adjust the bias.
Yeah. So this is actually an idea that comes out of academia. There is some prior work with sort of BrainGate clinical trial participants where they pioneered this idea of bias correction. The way we've done it, I think, is, it's very productized, very beautiful user experience where the user can essentially flash the cursor over to the side of the screen, and it opens up a window where they can actually sort of adjust or tune exactly the bias of the cursor. So bias, maybe for people who aren't familiar, is just sort of what is the default motion of the cursor if you're imagining nothing. And it turns out that that's one of the first sort of qualia of the cursor control experience that's impacted by neural non-stationarity.
Qualia of the cursor experience.
I mean, I don't know how else to describe it. Like, I'm not the guy moving.
Very poetic. I love it. The qualia of the cursor experience. Yeah, I mean, it sounds poetic, but it is deeply true. There is an experience when it works well. It is a joyful, a really pleasant experience, and when it doesn't work well, it's a very frustrating experience. That's actually the art of UX. It's like you have the possibility to frustrate people or the possibility to give them joy.
And at the end of the day, it really is truly the case that UX is how the thing works. And so it's not just like what's showing on the screen. It's also, what control surfaces does a decoder provide the user? Like we want them to feel like they're in the F1 car, not like the, some like minivan, right? And that really truly is how we think about it. Nolan himself is an F1 fan. So we refer to ourselves as a pit crew. He really is truly the F1 driver. And there's different, control surfaces that different kinds of cars and airplanes provide the user. And we take a lot of inspiration from that when designing how the cursor should behave. And maybe one nuance of this is, even details like when you move a mouse on a MacBook trackpad, the sort of response curve of how that input that you give the trackpad translates to cursor movement is different than how it works with a mouse. When you move it on the trackpad, there's a different response function, a different curve to how much a movement translates to input to the computer than when you do it physically with a mouse. And that's because somebody sat down a long time ago when they're designing the initial input systems to any computer, and they thought through exactly how it feels to use these different systems. And now we're designing sort of the next generation of this input system to a computer, which is entirely done via the brain. And there's no proprioceptive feedback. Again, you don't feel the mouse in your hand. You don't feel the keys under your fingertips. And you want a control surface that still makes it easy and intuitive for the user to understand the state of the system and how to achieve what they want to achieve. And ultimately, the end goal is that UX is completely, it fades into the background. It becomes something that's so natural and intuitive that it's subconscious to the user. And they just should feel like they have basically direct control over the cursor. It just does what they want it to do. They're not thinking about the implementation of how to make it do what they want it to do. It's just doing what they want it to do.
Is there some kind of things along the lines of like Fitts Law where you should move the mouse in a certain kind of way that maximizes your chance to hit the target? I don't even know what I'm asking, but I'm hoping the intention of my question will land on a profound answer. No. Is there some kind of understanding of the laws of UX when it comes to the context of somebody using their brain to control it? Like that's different than actual with a mouse.
I think we're in the early stages of discovering those laws. So I wouldn't claim to have solved that problem yet. But there's definitely some things we've learned that make it easier for the user to get stuff done. And it's pretty straightforward when you verbalize it, but it takes a while to actually get to that point when you're in the process of debugging this stuff in the trenches. One of those things is that any machine learning system you build has some number of errors. And it matters how those errors translate to the downstream user experience. For example, if you're developing a search algorithm in your photos, if you search for your friend Joe and it pulls up a photo of your friend Josephine, maybe that's not a big deal because the cost of an error is not that high. In a different scenario where you're trying to detect insurance fraud or something like this, and you're directly sending someone to court because of some machine learning model output, then the errors make a lot more sense to be careful about. You want to be very thoughtful about how those errors translate to downstream effects. The same is true in BCI. So, for example, if you're building a model that's decoding a velocity output from the brain versus an output where you're trying to modulate the left click, for example, these have sort of different trade-offs of how precise you need to be before it becomes useful to the end user. For velocity, it's okay to be on average correct because the output of the model is integrated through time. So if the user's trying to click at position A and they're currently at position B, they're trying to navigate over time to get between those 2 points. And as long as the output of the model is on average correct, they can sort of steer it through time with the user control loop in the mix. They can get to the point they want to get to. The same is not true of a click. For a click, you're performing it almost instantly at the scale of neurons firing. And so you want to be very sure that that click is correct, because a false click can be very destructive to the user. They might accidentally close the tab that they're trying to, do something in and lose all their progress. They might accidentally hit some send button on some text that is only like half composed and reads funny after. So there's different sort of cost functions associated with errors in this space, and part of the UX design is understanding how to build a solution that is, when it's wrong, still useful to the end user.
That's so fascinating, that assigning cost to every action when an error occurs. So every action, if an error occurs, has a certain cost. And incorporating that into how you interpret the intention, mapping it to the action, is really important. I didn't quite, until you said it, realize there's a cost to like sending the text early. It's like a very expensive cost.
It's super annoying. If you accidentally, if your cursor, imagine if your cursor misclicked every once in a while. That's like super obnoxious. And the worst part of it is, usually when the user's trying to click, they're also holding still because they're over the target they want to hit and they're getting ready to click, which means that in the data sets that we build, on average, it's the case that sort of low speeds or desire to hold still is correlated with when the user's attempting to click.
Wow, that is really fascinating.
It's also not the case, people think that, a click is a binary signal. This must be super easy to decode. Well, yes, it is, but the bar is so much higher for it to become a useful thing for the user. And there's ways to solve this. I mean, you can sort of take the comp-out approach of, well, let's just let's take 5 seconds to click. Let's take a huge window of time so we can be very confident about the answer. Yeah. But again, world's best mouse. The world's best mouse doesn't take a second to click or 500 milliseconds to click. It takes 5 milliseconds to click or less. And so if you're aiming for that kind of high bar, then you really want to solve the underlying problem.
So maybe this is a good place to ask about how to measure performance, this whole bits per second. What can you explain what you mean by that? Maybe a good place to start is to talk about WebGrid as a game, as a good illustration of the measurement of performance.
Yeah. Maybe I'll take one zoom out step there, which is just explaining why we care to measure this at all. So again, our goal is to provide the user the ability to control the computer as well as I can, and hopefully better. And that means that they can do it at the same speed as what I can do. It means that they have access to all the same functionality that I have, including all those little details like command tab, command space, all this stuff. They need to be able to do it with their brain, and with the same level of reliability as what I can do with my muscles. And that's a high bar. And so we intend to measure and quantify every aspect of that to understand how we're progressing towards that goal. There's many ways to measure BPS, by the way. This isn't the only way, but we present the user a grid of targets, and basically we compute a score, which is dependent on how fast and accurately they can select, and then how small are the targets. And the more targets that are on the screen, the smaller they are, the more information you present per click. And so if you think about it from an information theory point of view, you can communicate across different information theoretic channels. And one such channel is a typing interface, you could imagine, that's built out of a grid, just like a software keyboard on the screen. And bits per second is a measure that's computed by taking the log of the number of targets on the screen. You can subtract 1 if you care to model a keyboard, because you have to subtract 1 for the delete key on the keyboard. But log of the number of targets on the screen times the number of correct selections minus incorrect, divided by some time window, for example, 60 seconds. And that's sort of the standard way to measure a cursor control task in academia. And all credit in the world goes to this great professor, Dr. Shenoy of Stanford, who came up with that task. And he's also one of my inspirations for being in the field. So all the credit in the world to him for coming up with a standardized metric to facilitate this kind of bragging rights that we have now to say that Nolan is the best in the world at this task with his BCI. It's very important for progress that you have standardized metrics that people can compare across different techniques and approaches. How well does this do? So yeah, big kudos to him and to all the team at Stanford. So for Nolan and for me playing this task, there's also different modes that you can configure this task. So the WebGrid task can be presented as just sort of a left click on the screen, or you could have targets that you just dwell over, or you could have targets that you right click on. You could have targets that are left, right click, middle click, scrolling, clicking and dragging. You can do all sorts of things within this general framework. But the simplest, purest form is just blue targets show up on the screen. Blue means left click. That's the simplest form of the game. And the sort of prior records here in academic work and at Neuralink internally with sort of NHPs have all been matched or beaten by Nolan with his Neuralink device. So sort of prior to Neuralink, the sort of world record for a human using the device is somewhere between 4.2 to 4.6 BPS, depending on exactly what paper you read and how you interpret it. Nolan's current record is 8.5 BPS. And again, the sort of median Neuralink performance is 10 BPS. So you can think of it roughly as he's 85% the level of control of a median Neuralinker using their cursor to select blue targets on the screen. And I think there's a very interesting journey ahead to get us to that same level of 10 BPS performance. It's not the case that sort of the tricks that got us from 4 to 6 BPS and then 6 to 8 BPS are going to be the ones that get us from 8 to 10. And in my view, the core challenge here is really the labeling problem. It's how do you understand at a very, very fine resolution what the user is attempting to do. And I highly encourage folks in academia to work on this problem.
What's the journey with Nolan on that quest of increasing the BPS on WebGrid? In March, you said that he selected 89,285 targets in WebGrid.
Yep.
So he loves this game. He's really serious about improving his performance in this game. So what is that journey of trying to figure out how to improve that performance? How much can that be done on the decoding side? How much can that be done on the calibration side? How much can that be done on the Nolan side of like figuring out how to convey his intention more cleanly?
Yeah, no, this is a great question. So in my view, one of the primary reasons why Nolan's performance is so good is because of Nolan.
Mm-hmm.
Nolan is extremely focused and very energetic. He'll play WebGrid sometimes for like 4 hours in the middle of the night, like from 2 a.m. to 6 a.m. He'll be playing WebGrid just because he wants to push it to the limits of what he can do. And, this is not us like asking him to do that. I want to be clear. Like we're not saying, hey, you should play WebGrid tonight. We just gave him the game as part of our research, and he is able to play it independently and practice whenever he wants. And he really pushes hard to push the technology to the absolute limit. And he views it as like, his job really to make us be the bottleneck. And boy, has he done that well. And so that's the first thing to acknowledge is that, he is extremely motivated to make this work. I've also had the privilege to meet other, clinical trial participants from BrainGate and other trials, and they very much share the same attitude of like, they view this as their life's work to, advance the technology as much as they can. And if that means selecting targets on the screen for 4 hours from